Hello. In this video I'm going to discuss timers. The timers we like to use for instruction at BCIT are these old style Allen Bradley pneumatic timers. Probably not going to see a lot of these in the field, but they're kind of nice because we can visually see how they're working. They're a mechanical device. With these timers, it's just a timing module on a standard Series 700 relay, 4-pole relay. So this timer has two different kinds of contacts. You can see on the top unit here, there's a little dial that I can adjust the timing. And there's a way to take this module piece out, and we can change it from an on delay to an off delay. But right now this timer is an on delay timer, this timer is an off delay timer. Like I said, the bottom part of this timer is just a standard relay. So it's got 4 contacts, 2 normally open and 2 normally closed, and they work just like any relay contact. When I energize the relay, the open contacts close, the closed contacts open. When I de-energize the relay, vice versa, the closed contacts, the normally open contacts that have closed will open when the relay de-energizes. The normally closed contacts that have opened when it's energized will go back to being closed once it's de-energized. The difference is these timed contacts. So on this particular relay, we've got 1 normally open timed close and 1 normally closed timed open. And then up here we've got the relay coil. This relay just happens to be 120 volts AC, but we can buy coils anywhere from 24 volts AC DC up to 600 volts for this style of relay. Okay. The best way to understand timers is by looking at a timing chart. When you buy timers, and most of the time if you're going to buy a timer now, you would buy some kind of an electronic relay, which I have an example here. Here is some Telemecanique timers. You can see they're much smaller, but the idea is the same. We've got time contacts and instantaneous contacts. These particular ones are actually programmable, so we can get different kinds of functions. Something we don't really have time to go over. We just want to cover timers for now. Whenever you're buying these kind of devices, a lot of the time they're made offshore. So the instruction manual it's going to be multi-language, but one universal language is called the timing chart. So I've drawn the timing chart for a on-delay timer. So first, let's look at the symbols for on-delay contacts. There's 2 symbols that you might, or 2 kinds of symbols that you might come across. At BCIT, we like to use these 2 symbols. So this would be the symbol for the normally open on delay, and we'll call that normally open time close, or NOTC. And kind of the logic is this looks like an arrow, so that's the direction of timing. So think of it as that. So another way you could display this contact is with just a regular normally open contact, and then we'll put a TC right here. So again, normally open time close, or normally open time close. Here we've got just let me fix this. I don't know why I put a T there. Should be an N. Now we've got the normally closed timed open. So you can see that's a normally closed contact, and the timing is, that's the direction of timing, or this is going to go up when it times out. Or we could draw it just as a normally closed contact with TO. So normally closed, timed open. So in this example, I've got my timer coil. So this is my, let's say it's a 120 volt coil. So when I apply 120 volts to it, it's going to activate. So I'm going to say it's set for 3 seconds. We can set these pneumatic times anywhere from 1/10 of a second to, I think, up to minutes. So this timing wave, this is when it's de-energized, when it's off, and this is when I energize the coil. And you can see here in blue, when the line is down here, that means this contact's open. When the line moves up, it's closed. Now the normally closed contact is the complement of the normally open, or it's always opposite. When the normally open is open, the normally closed is closed, and vice versa. And just for reference, I've put the timing of the normally open instantaneous contact here. I could draw the normally closed, but obviously I ran out of room. But the normally closed would be the complement of the normally open, or it would be opposite. Now, important thing to understand about the instantaneous contacts of this pneumatic relay is it will change status when the coil changes status. So you can see when the coil goes on, the normally open contact closes. When the coil turns off, the normally open contact opens. And it follows the coil pattern exactly. Now the time contacts are different. With the normally open contact, remember this timer needs to be energized for 3 seconds before the time contacts will change position. Otherwise they will stay in their original position. So you can see here, we have energized the coil for a duration of 2 seconds, then we de-energized it. Well, you can see the time contacts, the normally open's open, and it stays open. It needs to be closed for 3 seconds before it will close. But again, the instantaneous contact closed when the coil was energized. So now we de-energize the coil. Now here we energize it, and then after a 3 second delay, this much time, now you can see the normally open contact closed, and look at the normally closed contact in green, it opened. So the coil stayed energized, and notice as soon as the coil de-energized, the normally open contact, which was closed, now reopens. The normally closed contact, which was open, reclosed. So what a statement we could make is on delay timers are timed, a normally open on delay is timed to close, but instantaneously opens. The normally closed timed open contact, there's a delay before it opens, but it instantaneously closes when the coil is de-energized. So again, we repeat it here. The coil gets de-energized, energizes again. After the 3 second delay, the contacts switch. And then we come here. Here we energize the coil for 1 second, and obviously 3 seconds did not elapse, and the time contacts remain in their normal position. But notice the whole time, the instantaneous contact closed and opened when the timer coil energized and de-energized. Now here I've drawn a very simple program for, or drawing for the timing of 2 motors. So we've got a standard stop-start circuit for M1. When I hit the start button, we energize M1, M1 contact closes. At the same time, TD1, which is an on delay, is set for 5 seconds. We have a normally open time close contact here. After 5 seconds, M2 will energize. When I hit the stop button, M1 de-energizes, the holding contact opens. At that same time, TD1 de-energizes. This is time closed but instantaneously open. M2 then stops. So if we were to draw a timing chart for M1 and M2, this time would be 5 seconds. M1 would start, 5 seconds later M2 would start. When M1 stops, M2 stops instantaneously. Hello, I've wired the circuit for the horn to sound for about, I think the timer's about 3 seconds. It's quite loud, so I'm just going to put it upside down in this box so we don't have to listen to it. We'll still hear it. And 5 seconds later, the motor's going to start. And the amber light will come on with the buzzer, and the green light will come on with the motor. Okay. So that was about 3 seconds. Here's our timer. I can, if I dial this, here's the adjustment dial right here. These are pneumatic timers. So all we're doing is there's a little needle valve and a bellows. So we allow more or less air to flow in or out. So when it's on an on delay, we're compressing the bellows, and there's a bit of a spring inside there. And this needle valve will allow that air to escape the bellows faster or slower. So I can adjust that needle valve. So I can go, if I go, turn it to the left, that will make the time less. If I turn it to the right, it will make the time more. So I'll just go a little bit to the right. I'll start it up. So it's not a linear adjustment. I adjusted it a little bit. It probably doubled in time. So I can make it shorter or longer. I made it shorter. Yeah, that's probably about 2.5 seconds. So we adjust the needle valve to allow the air to escape the bellows when we compress it. And when we set it for on delay, we can change this to an on delay timer by just taking these two screws out and flipping this module upside down. That turns it into an off delay timer. But the way it works is, instead of the needle valve allowing air to escape the bellows, it's when it's compressed, it adjusts how fast the air is allowed to return to the bellows. So it's a very simple electromechanical device. Problem with these, they might be susceptible to a change in temperature. If it gets really cold, the repeatability is not as good or as accurate as a electronic timer. But they're great for demonstrating timers. Hello, this video we're going to talk about off-delay timers. So on the board I've got the symbols for off-delay timer contacts. These two symbols are the NEMA symbols, so you might see these on a drawing. But I've also got the alternate symbols, which is the equivalent of the NEMA symbols. So here's our normally open. So you can see normally that's an open contact. Remember, contacts are in their de-energized state. And normally open, and it's time to open. The arrow goes down, so the timing is when it goes from closed to open. Now here we've got the normally closed contact. So normally closed, time closed. So the timing action is when it's going from open to closed. The alternate symbols are just a standard normally open contact with a TO here. So normally open, timed open. And here we've got a standard normally closed contact with a TC, or normally closed, time close. As with the on-delay timers, I think one of the best ways to understand timers is to look at the timing chart. So here I've got the timer coil. If we were using one of these pneumatic timers, it would be 120 volts AC. And the red line is when I energize the timer coil and de-energize it. So on and off. Here I've got the normally open contact. So when the contact's open, the line's down here. When the contact closes, the line is up here. And the same thing for the normally closed contact. And you can see the normally closed contact is always opposite the normally open contact. And for reference, I've got the normally open instantaneous contact at the bottom. And as we remembered with the on-delay timer, it follows the pattern of the coil exactly. So when the coil is energized, the normally open contact closes. When the coil is de-energized, the normally open contact opens. Okay, so all of these contacts are instantaneously changing when the coil is energized. So in the case of the normally open contact, when we energize the coil, it goes from open to close. The timing is when it goes from close to open. So if we examine the normally open first, you can see it closed when we energize the relay. But when we de-energize the relay, remember the timer set for 3 seconds. It needs to be off for 3 seconds, that's why it's an off delay, before the time contact, in this case the normally open, will open again. So here we energized it, then we de-energized it for only 2 seconds, and we energize it again. Well, the timer never timed out. It needs to be off for 3 seconds. So the normally open contact that closed when the relay energized stayed closed. But now on the second pulse, we energize the coil, we de-energize it, it stays de-energized for 3 seconds, then the normally open contact that was closed will reopen again. Then when we energize the coil, the open contact closes again, and again we de-energize the coil, off delay of 3 seconds, the normally open contact opens again. And you can see with the normally closed contact, it starts closed, instantaneously opens. It will not close again until the coil has been de-energized for 3 seconds straight. So that doesn't happen till here. Then the normally closed contact goes back to its normal position of close. But you can see it follows the pattern opposite the normally open contact. And you can see my instantaneous contact, well, it just follows the pattern of the coil. So here I've got a simple schematic of a timing circuit using an off-delay timer. So here we've got TD1, which is set for 5 seconds off delay. When I hit the start button, M1 energizes, M1 contact closes to seal the circuit in. The timer energizes, and we know this is normally open, instantaneously closed, but timed to open. So this contact closes, M2 starts. When I hit the stop button, M1 de-energizes, the holding contact opens, TD1 de-energizes, but then it starts its timing sequence. And remember, this one will stay closed until the timer times out, which is 5 seconds. Then it will open and M2 will stop. The timing chart looks like this. When M1 energizes, M2 starts as well. When we de-energize M1, M2 runs for 5 seconds before it stops. This is a common circuit for maybe a cooling fan on a hydraulic pump, where this is the hydraulic pump, M1 is the hydraulic pump, M2 is the cooling fan. We might want to leave that cooling fan running for 5 minutes. They get very hot. We've got a lot of oil being pumped, and we might want to leave that cooling fan on for a few minutes to let it cool off once you stop using it. But there's one fatal flaw of this circuit. And what might that be safety-wise? Well, the problem is if somebody sticks their hand maybe in that, gets close to that fan blade, or if that's a conveyor or something, and I hit the stop button, well, this motor's not going to stop right away. It's going to run until the timer times out. So this would be an unsafe circuit depending on the condition, but I can easily fix that by adding an emergency stop button. Let's make it a mushroom head button. We'll call it EM stop. And that might be a non-spring return button, so when I push it down, it stays open until I physically pull it back up.